Well, one thing that's come out of cognitive neuroscience is that perception is not simply, like in the case of vision, just a camera. It's not that we take a picture of a pre-existing world. Rather, it turns out that about a third of our brain's cortex is involved in visual perception. And that's a lot of processing power for just taking a picture. So what seems to be going on is that perception is really an active, constructive process. We're constructing the depths, the colors, the shapes, the motions, the textures that we see. And we're doing it very, very quickly. We construct all of this visual world around us in, when you open your eyes, it takes 100 milliseconds, a tenth of a second or so, to construct this whole visual world. So we have the feeling that it was there all along because it's so quick. So we actually fool ourselves. We're so good at this. We think we're seeing the world as it really is. We're seeing the world as we construct it. So that's one of the big insights from cognitive neuroscience. All of the above. So cognitive neuroscience has really made it clear that given the image at the eye, for example, and I speak about the eye because that's where I do my research, is in vision. The image at the eye is a two-dimensional image. So anytime you see in 3 dimensions, there are an infinite number of three-dimensional interpretations that are in principle compatible with the flat image at the eye. And that means that, in a mathematical sense, the problem can't be solved unless you bring in other constraints. And so that's where memory or something, or like experience, and it could be a species memory in terms of things that have been programmed into us evolutionarily, into the wiring of our brain. I'm now speaking in typical cognitive neuroscience terms where they speak of the brain as doing all of this stuff. So the idea would be that built into the synaptic connections in the brain are these constraints that allow us to take this mathematical problem of getting 3D from 2D, constrain that problem and actually get unique solutions, and also to get solutions for color and motion and shading and so forth. Absolutely. The world perceived as 3D is clearly a construct, and we actually know the rules well enough that we can, in virtual reality situations, make you see any 3D construct that we really want you to see, because we know the rules that are built into the system. So one of the things that we try to do is to understand these rules with such mathematical precision that we can build robotic vision systems so that computers can see. And we're pretty successful at that now. We can build robots that can drive cars down freeways pretty well without a driver. The construction of our perceptual world takes place in a cascade of neural representations. And each one can contribute its own kind of illusions. So it's not just really like 2 levels. If you think about it really carefully, there's many, many levels of neural representation, and there's wiring at each level. So there's wiring even in the retina, where there are these so-called center surround cells that have lateral inhibition, and those contribute to certain visual illusions we have. So if you have a sequence of stripes of gray, where it's really dark and then not so dark and not so dark until you get all the way to white, if you look at those, you'll see that the edges of those stripes look a little bit brighter at one edge and darker at another, something called the mock band effect. That's probably due to very early primitive processing in the visual system, in the retina, and maybe in primary visual cortex. But then as you go up the cortex, there's 2 pathways. There's the ventral pathway and the dorsal pathway. And the ventral pathway itself has several way stations along it. And so what you're going to get is at every way station, there are built into the neural wiring these constraints that we've probably evolved over hundreds of thousands of years to have for how we are going to construct color, construct edges, construct depth, construct motion, and so forth. So I wouldn't say that there's a 2-stage boundary here, like early and cognitive. It's more gradual. There's the very, very primitive, and then we see a sequence of representations until you get to what you might call the very high cognitive. Yeah. Well, that's one of the big questions. Now, the standard way that the field looks at this is to say, well, you know, in the case of vision, for example, you don't need eyes to have visual experiences, right? In fact, if you can close your eyes, and if we stimulate your brain, you can have visual phosphenes, so you can have conscious visual experiences. So in some sense, your consciousness of vision is not just a process of the eyes. And they would then say that that's evidence that it's the brain that's causing your conscious experiences. And so what we do have, and what the field is really good at right now, are literally dozens, perhaps even hundreds now, of well-defined neural correlates of consciousness, so that we know that this particular area of the brain has activity that's highly correlated with this particular kind of conscious experience. So, for example, area V4 of cortex, visual cortex, is highly correlated with color perception. So if you inhibit that area in the left, say the left hemisphere, with transcranial magnetic stimulation, then you will lose all experience of color in the right visual field. You will still experience color in the left visual field. So here's a case where we can just put a magnet, just touch it to your skull, and your conscious experiences changes dramatically, and we know where to touch it and what experience you will have. So there's clear correlation between the conscious visual experience that you're having and the changes in it and the cortical activity that you're, in this case, inhibiting. And if you do it on the right hemisphere side, then you lose visual, color in the left visual world. And the same is true for motion. So there's an area in lateral temporal area that does motion. So if you inhibit that with magnetic fields, you'll lose the ability to see motion in the right visual field. Everything is like a stroboscope. You see a person there, but you don't see the motion in between. Fortunately, when you take the magnet away, the motion comes back and the color comes back. So we have all these correlates, but the question then, the deeper question is, does the correlation imply causation? Is it the case that all these very strong correlations, and they're there, imply that the brain is causing the conscious experiences? Now, most people in the field think, yes, it's a slam dunk. The evidence is quite clear. But the problem we have is that no one has been able to give not only a scientific theory, but even any remotely plausible idea about how that could be. How could sodium, potassium, calcium ions running back and forth through holes in neural membranes be my conscious experience of the color green, or the smell of a rose, or the sound of a trumpet? There are a lot of so-called theories out there, and they'll have all these interesting neural mechanisms like reentrant thalamocortical loops, collapse of states of microtubules and so forth. But then when you say, where does the consciousness comes in, and they try to say, here comes consciousness, there's always a gap right there. There's a miracle that occurs between the reentrant thalamocortical loops and the appearance of consciousness. And no one has been able to fill that gap in with a scientific theory, not even with a plausible idea. So the idea that the brain causes our conscious experiences is widespread. Most people in cognitive neuroscience would say, of course, but the embarrassing fact is we don't have a single scientific theory and no plausible ideas. So I'm actually exploring a different direction. You could think of it as a search strategy. We're trying to find the solution to this problem. How is consciousness related to brain activity? 99% of the researchers are searching in one part of the search space, namely how could the brain cause consciousness? And we're not getting anywhere. So at least a couple percentage of us should go to the other part of the search space and try the other direction. Let's try consciousness first and see if it leads to brain activity, as a product. So go the other direction and solve the mind-body problem that way. It sounds implausible to my colleagues in cognitive neuroscience, but hey, as a search strategy, it's implausible for us all to look in one part of the search space. So let me go over here and look at this other part, and we'll see, who comes up with an answer. When I actually go give talks at universities and conferences, I present the mathematical model, and that raises the level of the conversation. If I didn't have that, I'm sure I would be dismissed without further ado. But with the mathematics, then they have to take it quite seriously. So my burden then is different from the burden of the neuroscientists who say that brain causes consciousness. They have to show how the brain or activities of the brain or properties of neurons or loops of activity cause consciousness without a hand wave, and they can't do that. My burden is to start with consciousness and without any hand waves get first all of physics. So I need to get classical relativity theory, I need to get quantum theory, and I need to get relativistic quantum theory as a starting point, and then hopefully an understanding of how neurobiology arises out of it. So for me, what I have to do is first say what I mean by consciousness. So I have to have a mathematical model. And I've presented one at this conference that I call conscious agent. And it's a very simple, and for a mathematician, my structure is actually quite simple. It's just 3 probability spaces, 3 maps between those spaces, technically Markovian kernels, and then just 1 counter that counts the number of experiences that you've had. It's a very, very simple mathematical structure. So I propose that that captures that plus then all the combinatorics, right, that you can get by interacting different conscious agents together, gives me a complete model for consciousness. So it's an empirical claim, and the claim is what I call the conscious agent thesis, that every aspect of consciousness can be represented as some system of interacting conscious agents. That's the claim. Very, very precise claim. And I present it in the same manner as Church-Turing thesis in the field of computation, where Turing came up with a model that's an abstract model of computation that's about as simple as my model. It's different, but he had, I think it's a 6 or 7 tuple Turing machine that he defined. I have a 7 tuple conscious agent that I've defined. And then Turing said that this simple 7 tuple that he defined, the Turing machine, is capable of representing any effective procedure, period. Anything that any computer could do could be done by his Turing machine. That's the Church-Turing thesis. If he's right, then the Turing machine provides this simple formalism which is universal for all computation. And theorems then can be built on that because it's so simple. So we get the halting problem and the busy beaver problem, all these things that are actually solved because of Turing's thesis. So we get computer science as a science and not just hacking because of this thesis. So I present my thesis, the conscious agent thesis, in the same spirit. Here's a fundamental definition of conscious agent. The claim is that every aspect of consciousness, every aspect, can be represented by a single conscious agent or conscious agents in connection, in interaction. And so it's an empirical thesis in the same sense as Turing's. It can be falsified. If someone can find some feature of consciousness that they show cannot be modeled by this formalism, I'm wrong. And I have to either abandon the project or change my formalism. I'll probably try to change the formalism first. But so then the other thing I have is what I call the thesis of conscious realism, which says that the world consists only of conscious agents. So I have one definition of conscious agent and one thesis, namely that the world consists only of conscious agents. And from that, so one definition and one postulate, I'm hoping by theorem and proof to get all of quantum physics and a complete model of consciousness. So to solve the mind-body problem in that way, without any hand wave, as pure mathematical consequences of the basic definition and postulate. So theorem, proof, all the way through. And what I presented in the talk this morning was I am able to show that the asymptotic behavior of conscious agents in interaction gives us precisely the same equations. The equations that describe that are mathematically precisely the same equations at one level that describe the wave equation of the quantum free particle. I'm able to put them in precise correspondence so I can read off how physical variables like position, time, energy, momentum are related to precise variables of the asymptotic behavior of conscious agents. So the claim is that particles in physics are our representation of asymptotic dynamics of consciousness. So it's the long-term, asymptotics means long-term. The long-term dynamics of consciousness is what we represent by these simple things, particles. That's the correspondence. So it's a precise mathematical claim. And that's the nice thing about having a mathematical formalism. These claims are extremely precise, and so they're extremely falsifiable. That's right. The particle would be a representation that a conscious agent uses as a shorthand to represent certain properties of this really complicated interaction of other conscious agents. Their interactions are quite complicated, right? But if you can summarize the long-term behavior of those interactions with just a few numbers, you get what we call a particle. So there literally could be an infinite number of discrete interactions among these agents. You can't deal with all that infinite complexity of all those discrete interactions. But you can say, what is the pattern long-term of those interactions? And that we can characterize with a handful of numbers. And that's what we call a particle. In physics, it's quite interesting. Point particles are a problem, right? Because especially if you try to build a theory of quantum gravity, as you go down to smaller and smaller spatial scales, the energies go to infinity and things blow up. So they've always known that at some point the notion of a particle is going to have to give way because it blows up on you. And that's one reason why they've gone to strings and membranes and so forth to break out of that blow up. But if you ask where do those come from, well, they'll say that those are the fundamental entities, that strings and membranes are just what is. They're the fundamental, they are vibrations in an 11-dimensional space, for example. So they are like, I guess they would think of them as oscillatory patterns or vibrational patterns in higher dimensional, objects, the various particles are. So, but they will still have to postulate these are fundamental. And that's true of any scientific theory, right, by the way. You can't explain everything. You always assume something, and then you explain something else. So you put, so to speak, all your miracles up front. This is what I'm going to assume. And the game of science is to make sure you put all the assumptions up front. Then after that, no more miracles are allowed, right? And then you have to get everything else without, a miracle. And that's the failure of the cognitive neuroscience approach right now to solving the mind-body problem. What they put up front is unconscious matter, space, energy, and so forth, neurons. And by the time they try to get to consciousness, they need another miracle to get there. I'm hoping to put up my definition of conscious agent as fundamental. So I'm just claiming, this is just the way the universe is. It's fundamentally conscious agents. Live with it. That's just the way it is. And this is how they interact. That's my postulate. Can I prove it? Well, I can try to disprove it. I can't prove it. But what I can try to do is to look at the implications of this theory, and in the scientific approach of falsifying things, I can try to be as explicit as possible about the predictions and then see if I can falsify them. So I make assumptions about conscious agents and just say that's the way it is. I don't know why. I mean, I didn't create this thing, but maybe I did. I don't know. But that's just the way it is, and then look at the implications and test them. So. My idea that conscious agents are fundamental and that space and time and physical objects are not fundamental is not the same thing as claiming that there's no objective world. It's claiming that the nature of that objective world is different than what most people think. Most of us think that the objective world is something that's spatio-temporal and has physical objects in it with mass and energy. I'm saying that there is an objective world in the sense that there's a world that would exist even if I, as a conscious observer, weren't here to observe it. There is, I'm happy to buy life insurance. That means I expect things to exist even after I die. So I believe in an objective world in that sense. But the objective world I claim is a world of conscious agents. And what we call the physical world, space and time and physical objects, is simply a really dumbed down representation of that. And the reason why we have that is each conscious agent has only a finite capacity. So if I'm a conscious agent, I have a finite capacity for experience and for decision and for action. That means that most of the rest of the universe, which is all conscious agents interacting, I can't represent in its full glory. In that sense, I'm unconscious of it. So, the neuroscientists will say that 99% of your brain activity is unconscious activity. Yes, that falls right out of this theory because conscious agents have finite capacity. So most of the processing of all the agents that constitute what I call me is beyond the consciousness of the agent that's talking to you. The agent that's talking to you right now has finite channel capacity. So almost everything else in the universe I'm either unconscious of, or I have really stupid low-level representations of it that we call space, time, and objects. Actually, one key part of the model is a mathematical thing called a kernel that goes from my experiences to my choice of actions. And it's that part of the mathematical model is my precise mathematics to capture what I claim is the ultimate free will of the conscious agent. So each agent in this theory has free will, but the best that we can actually do in mathematics to model that is to write down something called a Markovian kernel, which is just a list of probabilities. If I have this experience, then the probability I'll take this action is this action, and so forth. If I have this experience, then here's the probabilities for my actions. That's the best we can do in mathematical models for the fundamental reality, which is not mathematical, of ultimate free will. Absolutely. In fact, I've published in collaboration with others studies, fMRI studies and EEG studies. So my view does not mean that I don't want to do neuroscience. I do neuroscience, or I read neuroscience. I think it's extremely valuable. We need to get our data wherever we can. The question is, how do we interpret that data? Are we trying to interpret it in a simplistic way almost that says that these correlations show that brain activity causes consciousness? Or do we have to have a more sophisticated interpretation that says correlation does not imply causation? Standard thing in statistics, correlation does not imply causation, and it's really true here. Brain activity correlated with consciousness does not entail logically that the brain activity causes consciousness. Everybody would have to grant that. And then they'd have to grant that they've not had any success at actually getting a theory that goes from brain activity to consciousness. So at least give me a chance to try to go the other direction. One thing that comes out of this point of view is that we think of space and time and objects as the truth, and our perceptions, our visual perceptions, are the truth. But I've been doing evolutionary game simulations which show that true perceptions die or go extinct when they compete with perceptions that are just tuned to fitness. So evolution does not favor true perceptions, it actually drives them to extinction. That's evolutionary game theory. And genetic algorithms actually show that true perceptions never even arise. They just never even get on the scene. So that means that we need to reinterpret how we think about space and time and physical objects. And I've proposed this interface theory of perception that says our perceptions are like the desktop on your computer. If you have a computer with a little icon in the lower right-hand corner that's blue and rectangular for a file, that doesn't mean that the file itself in the computer is blue and rectangular. If someone thought that, that would mean that they really didn't understand what an interface is about. The blue color is not trying to tell you that the file really is blue. The shape of the icon is not trying to tell you the true shape of the file. In fact, color and shape are just the wrong categories for describing the file. And yet, the interface is useful not because it's true, but because it hides the truth. And it just guides behaviors to do the things you need to do. Write a paper, edit an image, and so forth. So the idea is that space and time, as we perceive them, 3D space and time, is our desktop. Physical objects are just the icons. They're species-specific icons that we've been shaped by natural selection through evolution to have, to allow us simply to survive long enough to reproduce in our niche. It's not about truth, it's about having kids. And so that's what it's all about. And we have to take our icons seriously. I mean, the big objection to my point of view here would be to say, well, Hoffman, if you think that train coming down the track is just an icon on your desktop, why don't you step in front of it? And after you're dead and your theory with you, we'll know that there's more to the train than just being an icon. And the point is, I won't step in front of the train for the same reason I wouldn't take an icon and drag it to the trash can accidentally or, casually. I don't take the icon literally. It's not blue, the file's not blue and rectangular, but I do take it seriously. If I drag that icon to the trash can, I could lose a year of work. Similarly, we've been shaped by evolution to have symbols like trains, snakes, cliffs, that we better take seriously. That's why we were shaped to have them. Don't take them literally. That's a logical error. Taking them seriously, yes, but that does not logically entail that we must take them literally. And yet most of us have the psychological urge to go from I better take it seriously to of course that means I have to take it literally. And that's the mistake.